রেকর্ডিং স্টার্ট করলাম, এখন আর দুষ্টামি না করি, ক্লাস শুরু করতেছি। Other tabs. So what was the so we did, আচ্ছা আমি নোটসটা বের করে আমাদের কাজ করা আগানোর সুবিধা হবে, so that we will have a definitive work procedure. কই যেন সেশন ক্লাস অলওয়েজ কপি সেকেন্ড, এখানে কই জানি ছিল, কোথা যেন তোমাদের নোটস দিছিলাম এখান থেকে। হাই হাই নোটস কই?
স্যার আপনি চাইলে
হ্যাঁ, এগুলো আমি কোন একটা টাইপও করছিলাম, সর্বনাশ। I did not know.
আপনি চাইলে মেসেঞ্জার থেকে নিতে পারেন স্যার।
এই যে আলাদা সব লেখা আছে লল টোটাল। ওকে সস, এটা তোমাদের দিয়ে দেবো, ব্যাপার না। ওইখানে আর এখানে একই জিনিস আছে। I think I did type it at some point of my life and then I absolutely forgot about it. Happens to the best of us. আচ্ছা, আমি তোমাদেরকে বেসিক্যালি কালকে আমরা লাস্ট ক্লাসে আমরা নিউক্লিয়াস পর্যন্ত আলোচনা করছিলাম, আমরা আজকে এখান থেকে শুরু করতেছি। Or I could download that note directly from your messenger chat. Anyway, ব্যাপার না, শুনো। আমি কিছু কথাবার্তা বলতেছি, আগে শুনে যাও, তারপর আমি আলাপ করতেছি। ফার্স্ট থিং হচ্ছে নিউক্লিয়ার রিঅ্যাকশনের বেসিক 3টা ভ্যারিয়েশন আছে। আচ্ছা, before I talk about nuclear fission, I would like to tell you one additional thing which is outside the scope of the syllabus, which is the fourth state of matter, which is called plasma. Plasma is a pretty interesting state of matter in the sense that আমরা primarily objective state করে জানি 3টা, একটা হচ্ছে solid, liquid and gas. In all of this state, the atomic structure of the substance remains intact, or it means atoms remain as atoms. If you keep an object at extremely high pressure and temperature to such an extent to such an extreme energy level for the substance, that at that energy level the entire structure of atom becomes dissolved. So at that scenario, the entire structure of the atom, including entire structure of the atom, becomes dissolved up, which means there are no exclusive atom or the typical shape of the atom, like there is a definitive nucleus and there are multiple electrons in different designated shell. This structure breaks up altogether. It becomes a whole hodgepodge mixture of nuclei and free electrons, and it's just a mixture altogether. They are so close to each other and they are just merged up. The atom structure simply doesn't hold up. This is possible for extremely high temperature and extremely high pressure. Let me give you an example of this one, because this would be necessary for us for the later part of the understanding. Try to think about it, that how does a star gets into formation in the space. Star formation আমাদের সিলেবাসে আছে, so এই পার্টটা star formation এখানে লিখছি। Star formation, ionization happens, half life time, star formation, এখানে star formation এই কিছু কোনা। আচ্ছা, স্টার ফর্মেশন এখানে লেখা নাই, স্টার ফর্মেশন মনে হয় আগেরটাতে লেখা ছিল। I hope star use of radioactivity. Wow, this is a really big PDF. Wow.
Sir.
Damn it, I wrote all the stuffs here.
The star formation এটা
star formation লিখেছেন স্যার, লাস্টে যে ফাইলটা দিয়েছিল ওখানে লেখা আছে।
ওখানে লেখা আছে।
I still think it's out to your own writings.
এখানে মনে হয় স্টার ফর্মেশন টুকু মিসিং আছে। দাঁড়াও, স্টার ফর্মেশন এখানে আছে,
আগেরটাতে আছে,
লাস্টের দিকে মনে হচ্ছে।
এখানে স্টার ফর্মেশন দেখতেছি না। আচ্ছা, স্টার ফর্মেশন তাহলে এখানে পরে আমাদের অ্যাড করা লাগবে। তাহলে আচ্ছা, স্টার ফর্মেশন নিয়ে আলাপ করতেছি। স্টার ফর্মেশনের বেসিক প্রসেসটা তোমাদেরকে বলি, দরকার একটা ভিডিও দেখাবো। আইডিয়াটা হচ্ছে, আচ্ছা না, আগে একটা ভিডিও দেখাই, তারপর আলাপ করি, তাহলে বুঝতে ইজিয়ার হবে। এগুলো তো সব আচ্ছা, প্রথমটাই দেখি। Okay, so they are doing so. Acha, so this is a lump of hydrogen particles. All of these individual illuminated dots represent individual hydrogen atoms, or maybe in molecular form if they have got the opportunity to merge up to case and make a covalent bond. So this figure is not drawn to scale because the hydrogen atoms would be extremely small compared to the space between them, but they have significantly make the atoms really large just to for us to understand their existence. So this figure is not drawn to scale. So we have this thing. What is going to happen? They are going to attract each other by virtue of the gravitational force that exists between them, and they are going to experience a resultant force inward or towards the center of this whole gas lump. This is what we call a gas lump in the space. Where did this gas lump come from? This shit আমি একটু পরে আলাপ করতেছি. Assume that this gas lump is available to us, and we're going to talk about how this gas lump is going to convert into a star and what's going to happen afterwards. So one of the things that I need to understand, let's say if you consider one specific gas particle, hydrogen atom that is located here, this hydrogen particle is attracted by all the hydrogen particles from all around the particle in all directions. But if you try to think about it, there is less number of particles on the outer side, more number of particles on the lower and on the inside side. So the total resultant attraction inward should be much bigger compared to the total outward attraction. Do you agree?
Yes, sir.
That is supposed to happen.
Yes, sir.
So this is the reason all of these particles for the each individual position, they experience a significant pull towards the center of this entire gas lump because of the resultant gravitational force that acts on the hydrogen atoms by the interaction of all the hydrogen atoms which are involved over here. So they start to squash on. So this entire thing start to squeeze in and they start to squash on. As they start to squash on at the center, the pressure and temperature starts to increase because this is very much similar like you are squeezing onto a locked up amount of gas from the outside. Continuously squeeze করতেছো. So as you are squeezing in the particles, work is being done by the own virtue of the system. And that work done is going to convert into, do you understand why work is being done? Because mass is being moved over a displacement. Resultant force is towards the center, particles are moving towards the center, so it means actually work is being done. So that work done would be converted into kinetic energy at the center of the star, where the gas, where the core or the central region of this gas lump will actually slowly start to get hotter and hotter and hotter. And they're gonna be an extremely high amount of pressure because of the squashing effect. Over the time, this will keep on happening, and at one point, the temperature of this whole thing is going to become so high, and the pressure will become so high that the structure of atom will start to break off. Structure of atom starts to break off means what? Try to understand. The basic structure of atom is basically empty space. It's like an empty stadium. There is if you consider the hydrogen atom is the simplest expression of mass. You have a proton and you have a single electron going around in orbit. That hollow thing makes up an hydrogen atom. So there's a huge amount of hollow space inside. Now, if you take a huge number of these hydrogen hollow atoms, put them in a container and start squashing in from outside really strongly, at one point they are supposed to break. And what should that breaking do? That breaking should cause all the particles to squash into each other, right? Because they have to succumb to the effect of that pressure. So that's what happens, and the entire atomic structure breaks off, and you get a total hodgepodge lump or mixture, a gaseous mixture of free protons and free electrons. They're all moving around without any definitive atomic structure. This is the state, what we call plasma, which is a fourth state of matter, only available at an extremely high temperature at a very high pressure. এই পর্যন্ত বুঝা গেছে?
Yes, sir.
Yes, sir.
Yes, sir.
আচ্ছা
স্যার
বলো।
স্যার হাইড্রোজেনের হলো অ্যাটম জিনিসটা বুঝি নাই।
I mean, think about the structure of a hydrogen atom. There is a very small nucleus, proton at the center of the atom, and there is a hollow space. And on the periphery or on the circumference of the hollow space, there is a single atom that is orbiting in a circular orbit. So তুমি যদি পুরো জিনিসটাকে একটা সিঙ্গেল স্ফিয়ার হিসেবে চিন্তা করো, that the total orbit path of the electron produces a sphere, imaginary sphere, that shape is what we call the hydrogen atom. But essentially it is mostly empty space, right? Because the proton is located at the center, which is very small, and there's a huge amount of empty space, and then there comes the first shell electron, which is going around the orbit. So the entire atom is basically not made up with physical substance. It is made up with mostly empty space.
Yes, I got it.
Okay. So I mean, for a regular scenario, this structure holds up because there is not enough external pressure, so the atom remains in equilibrium and it can exist on its own. But whenever you apply extremely high pressure at very high temperature, the particles collide with each other at so high intensity that that they cannot simply maintain that huge amount of interatomic empty space. I mean, the interatomic empty space. The empty space is not allowed to occupy. So they squash in and everything breaks off, and that becomes a whole mixture of free protons and free electrons. The atom simply doesn't exist because you do not allow that to happen for the limitation of space because of the high pressure that exists within the system. Mamun, তুমি কি AC off করে দিছো? I don't think so. Okay, never mind. Yes, Abdullah হাত উঠেছে বলো।
আপনি যে বলেন হাইড্রোজেনের যে নিউক্লিয়াই এন্ড ফার্দারমোস্ট ইলেকট্রন শেল, হাইড্রোজেনের মতো একটা ইলেকট্রন শেল, তো আমরা জাস্ট বলতে পারি ইটস অল নিউক্লিয়াই।
Yes, you can say the single electron, you can say the farthest most, you can say the closest electron, because there is only a one electron. Stating adding any adjective would be true for that electron. Okay, Fardin.
Sir, you said the atoms breaks, so that means that in the plasma state there is no element, right? We can say.
There is practically no element, but there is a catch to this. This is a pretty interesting question. The way we define any element, or to be more accurate, the way we define any isotope is by the constituents of the nucleus, right? For example, an aluminum atom is aluminum atom because it has aluminum proton number 20 na
30
30
13 sir,
13 আচ্ছা হ্যাঁ the nucleus that has 13 protons inside itself is called an aluminum nuclei. And aluminum nuclei আশেপাশে মোট কতগুলো ইলেকট্রন আছে সেটার উপর জাজ করতে হবে যে can we refer this to be as an aluminum atom or should we refer to this as an aluminum ion. But the name aluminum will be dictated from how many protons are there in the nucleus. So Fadin, তুমি যে কোশ্চেনটা করছো যে we cannot specifically say there is no specific element, that is not entirely correct. We can still say that there is specific element because by observing what each individual nuclei are made up from, we can say what element is there without the presence of the electron, because the electrons are all mashed up. The bottom line for your question is that the definition of an element is coming from the constituent of the nucleus. Element definition does not come from the constituent of the electrons.
Okay.
কিন্তু এখানে তো কোনো নিউক্লিয়াস থাকতেছে না।
না, নিউক্লিয়াস থাকতেছে তো। নিউক্লিয়াস গুলো সিঙ্গেল পার্টিকেল হয়, নিউক্লিয়াস গুলো ভেঙে যাবে না। বলে একটু পরে যেটা আলাপ করা শুরু করছে, হাইড্রোজেন ইজ গোনা ফিউজ ইনটু হিলিয়াম এন্ড দ্যাট হিলিয়াম উইল রিমেইন অ্যাজ হিলিয়াম। বাট হিলিয়ামের আশেপাশে দুটো ইলেকট্রন মিলে যে আমাদের একটা হিলিয়াম অ্যাটম হওয়ার কথা ছিল, সেটা হবে না। হিলিয়াম অ্যাটম যখন হিলিয়াম নিউক্লিয়াস যখন প্রোডিউস হবে, ওই হিলিয়াম নিউক্লিয়াসের মধ্যে দুইটা প্রোটন আর দুইটা নিউট্রন মিলে একটা টোটাল লাম্প হয়ে থাকবে, ওইটা ব্রেকডাউন হবে না। That would be a slightly bigger particle compared to a single proton, definitely. But that structure, that combined structure of two protons and two neutrons, that would be merged together. That will not be breakdown. I mean, the plasma state wouldn't be able to break down the nuclei. It will be able to break down the atom. বলো।
স্যার তাহলে প্লাজমা মানে এখানে একটা মিক্সচার অফ নিউক্লিয়াস আর ইলেকট্রনস এর মতো।
এক্স্যাক্টলি। মতো না, এক্স্যাক্টলি। শাফাত বলো, সাবির বলো।
স্যার এই যে অনেক গরম হয়ে যায়, that happens because of the friction between the individual nuclei and electrons and all the atomic subatomic particles, right?
Correct.
Sir, আমার একটা প্রশ্ন ছিল, hydrogen atom does not have any neutrons. The way we define element is by the number of subatomic particles in the nuclei of each of the atoms. তো এখানে যদি neutrons না থাকে, how is helium formed?
I'm going to talk about that in a bit.
Okay.
It used to pop up in our lecture after a while. Sadman.
স্যার আপনি কি আমাকে ডাকছেন?
তোমাকে কখন ডাকছিলাম?
ও না, ওই যে আমাকে শাফাত বলছিল।
আচ্ছা, sorry, Sadman, you are the thin guy. Shafat is the tall guy with goggles who is the cousin of Arif. Shafat, am I correct?
Yes, sir.
আচ্ছা, হ্যাঁ, ঠিক আছে। Sorry, Sadman and Shafat, I messed you up, but now I got it corrected. Never mind. Okay, drop your hand. আচ্ছা, continuing further. So, এটা হচ্ছে আমাদের হিলিয়াম সিচুয়েশন। এখন জিনিসটা হবে, এখনো পর্যন্ত কিন্তু আমাদের ফিউশন স্টার্ট হয় নাই। The atom structure that just got broken down, and we have a whole plasma state only at the core of the star. You have to understand that the entire star is not at the same level of pressure and temperature. At the center, we have the highest pressure and temperature build up. But on the other parts are still very much in gaseous state, and they're still squashing and keep on squashing. They will keep on squashing because of the gravitational force unless they are reverted backwards. Reverting backwards একটু পরে হবে, কেমনে হবে বলতেছি। So that plasma state is only happening at the very core of the star. At the very core of the star. And then this is going to keep on happening. This is going to move on further, and as this external hydrogen atoms are going to slowly keep on squashing onto the central core, the pressure and the temperature of the core is going to keep on increasing. That will really increase. And as the pressure and temperature will increase, the individual kinetic energy of the plasma particles, namely, let's say for this time we can talk about the protons, they will increase. The kinetic energy of the electrons will also increase, but electrons' kinetic energy simply would not play a role because electrons are not going to get merged in any case. Electrons happen to be extremely small, their mass is really small. So for the same amount of temperature and pressure, the actual kinetic energy content would be much higher for the protons compared to the electrons, because electrons have a mass of about 9.1 into 10 to the minus 31 kg, where the protons have about 1.6 into 10 to the minus 27 kg, nearly 10,000 times heavier compared to nearly 2,000 times heavier compared to electron. Not that, that's not my point. My point is, as the pressure and temperature will keep on increasing, the collision between the proton and proton is going to become more and more fierce or more and more powerful. One of the things that I really need you to understand, protons are positively charged particles. So physically speaking, if you try to visualize the collision between two protons in empty space, try to visualize that two protons are coming towards each other and they're about to collide with each other. Naturally, as they will slowly get closer to each other, they're going to start repelling each other at a much higher force because they have like charges. And this repelling force is going to try to slow them down. It's going to try to slow them down further, slow them down even further. If they don't have enough initial velocity to start with, they're going to get close to each other and reach a minimum distance between each other, at which they are going to come to stop, and then they're going to push off opposite away from each other. So they are not going to actually do a physical contact in the name of collision if they don't have enough velocity to begin with, because they'll be constantly repelling each other. If you really want them to smash into each other, like really collide into each other, that initial velocity to start with has to be significantly high, so that in the journey of hitting towards each other, they would be able to overcome that electrostatic repulsion due to the like charges thing, and they would be able to actually physically collide into each other. So to make that possible, to make the protons actually collide into each other, physically collide into each other, we would require a really, really high amount of pressure and temperature. We are talking about temperature and pressure within the, we are talking about temperature within the scale of 10 to the power 15, 17 Kelvin. So একের পরে 15টা বা 17টা শূন্য, এতগুলো শূন্য বসালে যত কেলভিন টেম্পারেচার হয়, অত টেম্পারেচারে গিয়ে আমাদের ফিউশনটা স্টার্ট হবে। Don't give a dot. Rub this. হলুদ ডট কে দিছ? ওকে। আচ্ছা, কি বলছিলাম?
Yes, sir. High temperature is needed for collision between the protons.
আচ্ছা, হ্যাঁ। So high temperature এই সিচুয়েশনটা হবে। So as the external gas molecules keep on squashing onto the core, the temperature and the pressure of the core is going to keep on increasing, and eventually there will come a point where the temperature of the core reach to such a high value that the protons are going to really collide into each other and actually hit each other, physical contact, and now they are going to start to break into smaller pieces and recreate themselves into other pieces. So there is a much deeper explanation to this, which is called the quark structure. Quark structure তোমাদের O level syllabus নাই, AS এ আসবে, so এটা আমি আপাতত বলতেছি না. What I want you to understand, যে the protons are going to, in the process of collision between the protons and protons, some of the protons are going to convert into neutrons by some process. What that exclusive ECBC part of that process is not discussed in our O level, so I'm not getting into that. So what is going to happen in this process? Let me just write this up in the MS Paint. That some protons are going to get converted into neutrons. So the more summarized version of the nuclear fusion process can look like this: that 4 protons, this is the proto symbol for proton, or you can also write 4 hydrogen, that also works. These are going to collide with each other in some specific sequence or mechanism to produce 1 helium nucleus. So this is the overall reaction that happens, but it doesn't happen in a single stage. There are 4 different stages over here. প্রথমে proton proton থেকে হয় হচ্ছে তোমার deuterium, deuterium থেকে হয় হচ্ছে helium 3, helium 3 থেকে তারপর হয় হচ্ছে helium 4. So there are multiple stages inside it, but for the sake of simplicity তোমাদের সিলেবাস এইটুকুই আছে। এটা হচ্ছে আমাদের বেসিক ফিউশন রিঅ্যাকশনের বেসিক নিউক্লিয়ার প্রসেস। সো এসেনশিয়ালি এখানে কি হচ্ছে দেখো, এটার ভিতরে কি আছে? This is made up from 2 protons and 2 neutrons, and this is basically represent 4 proton. তার মানে হচ্ছে in the process of nuclear fusion, actually 2 protons will convert into 2 neutrons. That's going to happen. So I can give 1 1 and 1 0 over here. This is actually what happens in the nuclear fusion process. For one helium to produce 1 helium at 1 helium nucleus, we have this much conversion. So by some mechanism, protons convert into neutrons, and neutrons and protons are interconvertible, by the way, because we're going to see that beta decay after a while, and in that scenario you'll find out that neutrons are going to be converted into protons and give rise to beta decay. So we're going to talk about that in a bit as well. So this is going to happen, and as a result the helium is going to be produced. So what is really important, that whenever this will produce, this reaction will give rise to an enormous amount of energy. Individual reaction will not give a large amount of energy. The individual energy out from a single production of a helium atom, helium nucleus, is very small. But we are talking about billions and billions and quadrillions of particles continuously smashing into each other and undergoing reaction at the same time. So the total amount of energy will reach very high, and and this process practically feeds on itself. মানে হচ্ছে কিরকম যে let's say the external gas is squashing onto the central core and increasing the pressure. At one point, let's say one fusion process happens. That single fusion process will release a pretty high amount of energy within a plasma core that is already extremely heated up. This will lead up the neighboring particles to undergo fusion process, and this fusion process will almost immediately start up onto the whole plasma, because whenever you are starting to produce energy out of its own self, then it can self-heat itself. এতক্ষণ পর্যন্ত হিটিং হচ্ছিল এক্সটার্নাল পুশিং এর জন্য। Once the fusion process gets started, the core can produce its own heat energy out of the nuclear fusion process, and it starts to become extremely hot, and that's when the star starts to light up. This is the point where the star start to produce visible photons, which is light or electromagnetic waves, out of its core, which starts to go outwards. Now comes the secondary factor. Secondary factor মানে হচ্ছে, when the core starts to produce its own heat, it heats up the entire neighboring gas molecules, because heat is going to be radiated outwards from the core outwards because of the nuclear fusion process. And whenever you heat up a certain amount of gas, its natural tendency is to expand, right?
Yes, sir.
Whenever you heat up some gas, its natural tendency is to expand. So
Yes, sir.
as up till this point, before the fusion got started, the only working
Sir.
force on the একটু শেষ করি, একটু হাত উঠাও, আমি একটু শেষ করি, তারপর কোশ্চেন নিব। আবার একটু একটা পার্ট পর্যন্ত বলে নেই। Up till the point of fusion getting started, before the fusion got started, all the neighboring or the surrounding hydrogen atoms were attracted towards the center due to the effect of gravitational force. But whenever the fusion at the core gets started, all these gas particles are going to start to absorb heat that is radiating out from the core of that whole gas lump. This will heat up the neighboring gas, and because of the gas property, they're gonna have a tendency to expand out. So now we have 2 opposing forces in work. Gravitational force is trying to squash the particles towards the center. The heating effect, or this is in celestial term, we also use the term radiation pressure. That's a new term. তোমরা basic heating effect বললে হবে। The heating effect is going to try to expand out the gas lump. At a certain point, these 2 forces balance each other out, and the entire hydrogen lump receives a fixed diameter. Fixed diameter means this is the case where the internal pull due to gravitational force perfectly balances out due to the external expanding tendency due to the temperature of the gas. This is the level. When this equilibrium is reached, we say a star is born. এই পর্যন্ত হচ্ছে স্টার বর্ন হওয়ার প্রসেস, এবং এই পয়েন্ট থেকে শুরু করে এরপর আরো ফার্দার অনেক কিছু হবে। the total mass is going to reduce and eventually the star is going to become expanded at some point and it's going to undergo type 1 supernova or type 2 supernova, which can lead up to different type of end product. For example, we can have a white dwarf, then we can have a black hole, or we can have a neutron star. These are the three different output that can come from three different type of mass class for the hydrogen lamp. But you don't have that part in your syllabus, so I'm not going to put that in your head. But your syllabus have how a star is formed. একদম শুরু থেকে শুরু করে till the point when the diameter of the whole hydrogen lamp becomes a stable value. কখন stable হবে? When the stability will come, when the inward pull of the gravitational force is perfectly balanced out by the external expanding tendency due to the temperature gain from the nuclear fusion process. These two are balanced out. The entire hydrogen lamp will receive a uniform or stable diameter. This is the point of time where we say a star is born, or formation of a star is finished. Now the star will start its regular life cycle and do some other stuff through its life cycle, which is a different story, not part of your syllabus. So I'm available this year. I'll take questions. Odomo.
স্যার এই সেম প্রসেসে নিউক্লিয়ার বম্ব কাজ করে না?
Not essentially. Nuclear bombs are typically work with nuclear fission, which is a different case, which I'm going to discuss in a while. But we can also make fusion bombs work, which are much too powerful compared to fission bombs, but less hazardous compared to fusion bombs for the long-term effect. Why? ওটা আমরা একটু পরে আলাপ করব। Typical nuclear bombs work in nuclear fission or chain reaction, not in nuclear fusion. But nuclear fusion bombs can also be designed and produced. Russia produced a couple of them. Tsar Bomba is one of those bombs. They have extremely high power of capability for destruction, but they have less long-lasting effect, unlike nuclear radiation. But so yeah, did I get your question answered?
Sir.
আচ্ছা, বিপ্লব বলো।
Sir, how does the star get the energy from itself? এটা নিয়ে সমস্যা আছে।
The star gets its energy from itself because of the gravitational force that exists between each individual hydrogen atom to begin with. I mean, because of gravitational force, because the force exists because of the mass property. I mean, anything that has mass will be subject to gravitational force. The entire gravitational force is gonna keep on bringing the object closer. So let me give you a very simple example to make sense with you. Let's say, above the ground, we are holding a piece of brick above. Let's say at 1 meter above the ground, we are holding a piece of brick. If we allow the brick to fall down by the effect of gravity downwards, shouldn't its GP convert into K?
Yeah.
That is exactly what is happening over here. All of this.
এই পার্টটা একটু রিপিট করবেন, মানে জিপি টু কে কিভাবে ওই পার্ট?
We are holding a brick 1 meter above the ground. If we let go of the brick, it's gonna fall down. So what energy conversion are you gonna have?
GP to K.
Exactly. So if you think that each of these hydrogen atoms which are shown in this video, let's say each of these hydrogen atoms which are shown in this video, they all have a significantly high amount of GP because they're all trying to reach towards the center, because the forces are working towards the center. As they're gonna fall farther closer to the center, more part of their stored GP will be converted into K. That's where the energy is coming from. Biplo, তোমার question answer পাইছো?
Yes.
But then all of that K then accumulates to like cause the initial energy of the nuclear fission or something.
Not all of them, only a small part, because the entire hydrogen lump does not become plasma. Nuclear fission only happens at the core where the temperature and pressure is really high. So this part undergoes nuclear fusion, not the whole part. So the energy essentially is coming from all the particles because they are all squashing onto this thing, but the actual conversion happens only at the center of the star, which is called the core of the star.
মানে যতটুকু energy like that's only enough for like the core of the to like nuclear fusion
Exactly. Not all over the star, but the entire star looks glowing because the energy that comes out of this core, which is happening due to the nuclear fusion process, that is gonna illuminate. So as these photons come out, they pretty much illuminate all of these hydrogen atoms.
Oh, thank you so much.
Sure. আমি টেম্পারেচার গ্রেডিয়েন্ট একটু দেখাই তোমাদেরকে, তাহলে তোমরা আর একটু ভালো বুঝতে পারবা। পটর পটর শব্দ করতেছো কে?
তো স্যার একটা কনফিউশন ছিল স্যার, এই প্রোটন গুলো কখন স্যার ওই নিউট্রনে যে ইয়ে হয় ট্রান্সফর্ম হয় স্যার, এটা বুঝিনি ঠিকভাবে।
অনেক কম তো।
এটা কেলভিন।
ইয়াসির, এটা সারফেস টেম্পারেচার।
হ্যাঁ ওইটাই বলতেছি।
এইটা দেখো পড়া যাচ্ছে?
স্যার বুঝে যাইতেছে না একটাও।
দেখো
স্যার কুইজ একটা ভিডিও আছে, এটা অনেক ইউজফুল।
আমি বুঝতে একটা ভিডিও দিন নিলে এখন পরে আমাকে সেটা আবার কপিরাইট ক্লেম দিয়ে আমার ঝামেলা ফেলাবে, ওই জন্য আমি ওটা বের করতে যাচ্ছি। আমি এই ফিগারটা আচ্ছা এই সার্চ ইমেজ অ্যাজ সরি সেভ ইমেজেস না সরি I want to search this image. Search the web for this image. Large. How large is this?
স্যার আমরা তো জুম করে দেখতে পারতেছি না।
It's the large না, it large কেমন হলো?
স্যার ওয়ার্ডে নিয়ে গিয়ে টেনে বড় করে।
এই যে এখন দেখো, this should give you some idea. এইটুকু হচ্ছে গ্যাস, অ্যাকচুয়াল গ্যাস। এখানে এখনো গ্যাস, এই লাল পার্টটা যেখানে কনভেকশন জোন লেখা আছে এটা এখনো গ্যাস আছে। এইখান থেকে শুরু হচ্ছে প্লাজমা, এই পুরোটুকু হচ্ছে নর্মাল প্লাজমা। এই প্লাজমাতে নিউক্লিয়ার ফিউশন হচ্ছে না, যতটুকু হলুদ দেখানো এইটুকুতে নিউক্লিয়ার ফিউশন হচ্ছে। So if you think about the radius, this is radius in terms of this is the entire radius given in as 1. This is the 30%, 40%, 60%, 70%, 80%, 90%, 100%. So ওরা এটাকে exact value হিসেবে দেয় না, proportion হিসেবে দেখাইছে। Then the density of this thing is given in this format, and here is the temperature, millions of Kelvin. At the end of the nuclear fusion process, the temperature is 8 million Kelvin. 8 million মানে হচ্ছে 8 এর পরে 6টা শূন্য। Then 4000 Kelvin, the borderline for the plasma border is about 2 million Kelvin, and it goes on like that. So this is the part where the nuclear fission is actually happening, which is illuminating the entire star, because the energy output from this process is extremely huge, like oh my god type of huge. Tomar question answer পাইছো?
That means, sir, the nuclear fusion process is an exothermic process which releases an insane amount of energy, which causes a chain reaction of more nuclear fusion, right?
I wouldn't be preferring chain reaction.
The heat released from one fusion.
I would not prefer the word chain reaction, because the way we human beings have defined the idea of chain reaction does not entirely adapt to the idea of nuclear fusion. For a star it does, but for artificial creation it does not. Can এটা কাজ করবে সেটা আমি পরে বলতেছি। Apart from the two words chain reaction, rest of the discussion that you put down was absolutely correct. And কেন chain reaction পার্টটা কেন হবে না সেটা আমি পরে আলাপ করব, don't worry.
স্যার আমার সাবঅ্যাটমিক পার্টিকেল গুলোতে প্রবলেম ছিল, এই প্রোটন নিউট্রন এর নাম্বার গুলো নেই, তো ওই পেইন্টে যাবেন যেখানে লিখেছেন। স্যার এই নিউটনে 10 আর প্রোটনে 11 টাতে কনফিউশন। আপনি হাইড্রোজেন 11 উপরে যেটা লিখেছেন সেটাতে প্রবলেম নাই। প্রোটনের এই 11 নাম্বার গুলো কি রিপ্রেজেন্ট করে?
আচ্ছা এগুলো একটু পরে বলবো, আসবে, don't worry. I'll come to it. Fine বলো, Khankar Fahim.
Sir, could you re-explain how like the inward gravitational pull and the outward expansion of heat eventually balances out and forms a normal star?
The tendency of the external gaseous molecule is to squash onto the center of the star because of gravitational pull. As they keep on squashing, the temperature at the core keeps on increasing. At one point you have the fusion process getting started, which further heats up the core and the entire star. So whenever you heat up a certain amount of gas, its natural tendency is to expand out. So because of the temperature gain that happens from within the star, that hydrogen gas lump prefers to go expand outwards. because hot gas tends to expand. So it does not physically expand because as the, try to visualize that the star is going to slowly ascend. Let me just play this video. This might actually play out better. Dekho. You see, that's the plasma. Particles are merging in, producing the core. So going further, zoom in. The spinning action happened due to the centripetal force. ওইটা পরে আলাপ করতেছি, ওইটা তোমাদের সিলেবাসে পার্ট না, জাস্ট দেখতে থাকো।
স্যার সেন্ট্রিপিটাল নাকি সেন্ট্রিফিউগাল কোনটা বলেন?
সেন্ট্রিপেটাল বলছি, and I meant it.
Okay, sir.
Sure.
It looks like a galaxy.
This is exactly what happened. This is a simulation of this is a made up thing in a computer environment from the information that scientists have gathered from the outer space over the years of research. So this is actually a simulation. So keep observing. All of these small tiny dots you are seeing, they are hydrogen atoms which are still getting attracted towards the center, but at the center the pressure is really high. That's where the glowing thing is happening, which is the plasma, and it's going to keep on happen further. I don't know how this video ends because I'm seeing it also for the first time. I hope they actually show the final star. I really hope they do. Is that it? That's it.
Yes,
Dang.
এই জন্যই তো জিজ্ঞেস করছিলাম।
The star is gone.
তাহলে তো হলো না। আচ্ছা, এখানে লাভ নাই। বলো।
মানে স্যার, why? I mean, you said all the hydrogen particles or the broken down hydrogen particles they attract to the center, sir. What starts this?
Each of them contain
gravitational attraction.
And T-star.
এটা কি একটা নেবুলার ভিতর হচ্ছে?
হ্যাঁ, usually yes.
স্যার,
আচ্ছা শোনো, স্টার ফরমেশন এক্সাক্ট ভালো অ্যানিমেশন পাইলে আমি যেভাবে বললাম সেটা পাইলে তোমাদেরকে আমরা পাঠাবো।
স্যার কপিরাইট ক্লেম তো করার জন্য আপলোড করতে
আগে দেখছিলাম কোন এক জায়গাতে, সো ইউটিউবে এটা আছে, কোথায় আছে আমার খুঁজে বাই করা লাগবে। সো I'll hopefully give you this, don't worry.
Sir,
বলো।
Is nuclear fusion a continuous process? Does it keep on happening?
As long as
all the hydrogen.
As long as you have enough temperature and pressure available at the core due to the gravitational pull of the stars, because as the fusion process keeps on happening, mass converts into energy following the Einstein's famous formula E equals to mc squared. So because of that formation, slowly over time the star loses mass, which means the gravitational pull slowly becomes weaker and weaker and weaker. At one point the gravitational pull becomes so weak that it cannot hold down the star towards hold down the total gas around the star towards the center anymore, and that's when the death process of the star gets started.
Hello everyone. Your luxury after ever. Specialists had storm an element of stunned astronomy press in review and understand. As gravity continues to pull the infant star together, the center of the collapsing ball of gas gets hotter and hotter until temperatures at the middle reach an astonishing 10 billion degrees Celsius. At this temperature, protons can collide so forcefully that nuclear fusion can occur. Physicists call this reaction fusion because protons that originally formed in the nucleus fuse together to make the nuclei of heavier atoms. In a star like our Sun, 4 atoms of hydrogen eventually combine via fusion to make a heavier nucleus of helium. What makes
These are the stages that I talked about, which are not included in your syllabus. So you only have the initial stage, 4 hydrogen atom, or 4 proton particles, which are ultimately converted into helium. So in between stage to the syllabus, but this is the actual process by which it happens. So there are multiple stages of this conversion.
Makes fusion inside of a star so useful is the transformation of the element, making it into a slightly heavier one, and this releases energy. The combined energy released by billions and billions of individual fusion reactions flows outward from the star's core. Some of it eventually emerges from the star's surface as light. The pressure of sunlight, along with particles blown off the surface of the newborn star, sweep away from the surrounding cloud of gas and dust, and therefore a star is now born. Most stars are born in groups. These are often called star clusters. Clusters like this that stay together allow us to track the stories of the stars, while less massive clusters will simply dissolve because of the lack of gravity. These stars in less massive clusters will eventually mix into the general population of the Milky Way. Most stars will simply wander the galaxy until they get into a stable orbit, very similar to how a planet orbits a star. The outward push from nuclear fusion in its core is now nicely balanced with the inward push of gravity.
This is the answer for your question. Ke jono korsila? Khankar Fahim. You asked the question that how does two things get balanced? Did you see it now? বুঝা গেছে কি?
Yes, sir.
কোর্সটা কি দেখিয়েছিল দেখতে পারি? Nuclear fission.
The process is nuclear fusion, but the actual physical happening is because of the tendency for a gas to expand outwards because of temperature gain. That is the actual underlying description. But the key process for which that is happening is nuclear fusion. That's why they are showing it as nuclear fusion. So nuclear fusion at the bottom of the line, nuclear fusion causes the star to give an expanding tendency, but the gravity causes the star to give an inward squashing tendency. These two balances out at a certain point.
In its core, it is now nicely balanced with the inward push of gravity, and the star remains in this balanced state for about 90% of its lifetime. This is now at the stage that the Sun is now in. It's been at this stage for almost 5 billion years, and it will continue to do this for at least another 5 billion years more. Having a stable star is thought to be critical to the development and evolution of life. How long a star lives depends on how much material or mass it has. Massive stars have a lot of gravity, which makes the centers extremely hot, and therefore they tear through their hydrogen atoms extremely fast and exhaust their fuel very quickly. The most massive known...
In this case, fuel means the hydrogen availability, because hydrogen is converting into helium. So hydrogen is considered the fuel for the fusion process to occur. Output is what is considered to be the helium. So fuel essentially in this case means the availability of hydrogen nuclei or protons.
Stars last only a few million years. The core of the lower mass stars, like our Sun, is a lot less hot and burns its fuel a lot more slowly. This means that our star can last for billions of years, rather than just millions. The lowest mass stars, known as the dwarf stars, burn very, very slowly, and they may last more than 100 billion years. This is much longer than even the current age of our universe. Nevertheless, the core of every star eventually runs low on nuclear fuel. At this point,
eventually, everyone runs low on fuel.
The star experiences a bit of a crisis. Gravity is still compressing the star, but the outward push of fusion begins to suffer. A complex series of events then occurs, which leads the star to collapse on the inside whilst it swells up on the outside. As the outer layers of the star grow larger, they cool off and become reddish in colour. A red star is cooler at its surface than a white star. Astronomers call these type of stars red giants, and they can become as large as the orbit of Mars or even Jupiter. A particularly dramatic example of a red giant is the star Betelgeuse. It is 425 light-years away from Earth in the constellation of Orion, so it's astronomically quite close. It has now grown to be 600 times larger than our Sun, and were it to replace our Sun at the centre of the Solar System, it would completely swallow the orbits of all of the inner planets. But all red giants eventually do find a new source of fuel, but the star is never quite the same again. Some of its outer layers are permanently lost, and its resumed inner stability is only temporary. The lifetime of stars splits into two branches. The low-mass stars, which is our Sun, have only a limited ability to squeeze their cores to continue the fusion processes. They experience a period of instability, where their outer layers lift off. This period of instability for those stars produce some of the most beautiful objects in the night sky. As a star shreds its outer layers, the gas inside of it is illuminated by the light of the collapsing star and glows in an array of colours. These are the last gasps of a dying star. These objects were named planetary nebulae because they resemble disks of planets, although we now understand that they have no connection at all to planets. But the name, of course, has stuck. So on the other hand, high-mass stars have significant pressure and temperature at their cores, and this means that they can continue the fusing process. By using these newer, heavier atoms that they formed earlier, helium, carbon, and oxygen are each in turn becoming fuel to make more energy for the star, and this is fighting against the gravity.
This is the key part, that for low mass star, the only nuclear conversion that we can achieve is hydrogen into helium. That's it. And when the hydrogen gets finished, there is not enough pressure for the gravitational pull to further continue the fusion process, and the star spreads out and it pretty much goes into its dying stage. But for more massive star, which started with the much bigger hydrogen lump, they have significantly large amount of gravitational force. So as a result, the temperature at their core are extremely large. So in their regular life cycle, which is about 1 million years, because they run out of their fuel pretty fast, because the nuclear fusion process is really vigorous and fast, they can produce secondary nuclear products. Secondary nuclear products means products which are output from the fusion of helium-helium. Now, what do I mean by this? Try to understand this thing. The amount of temperature you would require for two protons to collide into each other, you have to overcome the repulsion of two proton particles. But if you want to collide two helium particles into each other, you have to overcome the repulsion of two helium particles. Now, two protons have a charge of +1, +1. To overcome that thing, you would require a minimum speed of the two protons. If you want to overcome the speed of, if you want to overcome the repulsion of two helium particles, you are trying to overcome the repulsion between two helium nuclei, which are +2, each. So the required amount of temperature for, or which eventually turns into velocity of the charged particle of the nuclear particles, has to be extremely high, like super high. That super high temperature is possible only if the original mass of the star was extremely big. That's why in the regular life cycle of within those million years, these stars can produce the merging of helium, which is called the secondary fusion, and that can give us the output of carbons and oxygen, which are present into the core of the more massive stars, and eventually it happens further down the line.
And this keeps the star stable, at least for a brief time. Eventually, however, the massive star's core becomes composed of simply iron, which sets off the final collapse and the catastrophe. When low mass stars
iron is the last outcome of any fusion process. Eta keno sheta pore bolbo.
Stars die, they collapse under their own weight until their centers act in the same ways like a solid. A star like our Sun will collapse at the end of about twice the size of Earth. These white-hot dying stars are called white dwarfs by astronomers. Perhaps the best-known white dwarf orbits the brightest star in the sky, Sirius. but it requires quite a large telescope to see it. Massive stars are very different in their ending. When the core of a massive star collapses, its powerful gravity takes it right through the white dwarf stage to produce one of two extremely bizarre objects, either a neutron star or a black hole. In most cases, the rest of the star blows up in a gargantuan explosion called a supernova. These explosions produce so much energy that the star can briefly become brighter than the entire galaxy in which it's located. This is approximately brighter than 100 billion suns. Extreme versions of supernova explosions are sometimes referred to as hypernovae, and these produce gamma-ray bursts. The most famous supernova in history was in July 1054. Records of this still survive, from China all the way to North America. Seen today, roughly 1,000 years later, its remnant is called the Crab Nebula, and it is one of the most interesting objects in the night sky. It can be found with a good pair of binoculars or a small telescope in the constellation of Taurus. Near enough every star leaves a corpse. Star corpses come in three bizarre varieties. A white dwarf fades away as billions of years pass. Since no energy is being produced inside of it, and light is escaping off into space, the star's corpse slowly cools down and becomes black as space. Astronomers call these corpses black dwarfs. A supernova explosion leaves behind a far more compressed corpse. The violent end to a massive star produces so much pressure that the star's core experiences a remarkable subatomic change. Electrons, that are negatively charged particles which orbit the nucleus of the atom, are actually squeezed into the nucleus. The electrons join with the protons to become neutrons. The process also removes all the space within the atom, leading to a fantastic compression of a star's remnant. To make something as dense as a neutron star.
So what is happening? The orbital electrons are getting merged into the nucleus, converting all the protons into neutrons. Beauty of this process is that protons have repulsive forces due to charge, but neutrons have no charge, so they don't have any repulsive force. If you have a lot of neutrons available in a single space, they can occupy, they don't have to have any space in between them because they don't repel each other, so they are pretty much, they will be like clamped up within a small amount of space. That's the beauty of having a, that's the beauty of making everything into neutron, that you can accommodate all of those particles in a very close confinement without any allowed space in between them. As a result, all of this thing which used to be present at the core of the star, iron or oxygen or carbon or helium, everything that ultimately got to exist in the core of the star, they undergo this conversion and everything becomes neutron, and they pretty much clump up together to have a very small volume but an immensely high amount of mass. That's what is called a neutron star. He's going to talk about the neutron star in a while. So let's go forward.
On Earth, we would have to take all the people in the world and squeeze them into the size of a raindrop. But I wouldn't really. And as a neutron star on Earth, we would have to take all the people in the world and squeeze them into the size of a raindrop. But I wouldn't really recommend that. If the dying star is especially massive, the remnant becomes a completely collapsed object, known as a black hole. In these objects, gravity is so strong that nothing, not even light, can escape. Space, time, matter, and energy are all trapped within a tiny region. Understanding the behavior of black holes is one of the great frontiers in the area of astronomy. So, by looking at a life story of a star, you might be thinking to yourself, how does this interact with human life here on Earth? What's the difference between life and death and previous generations of stars when it doesn't have anything to really do with humanity? The thing is, stars have a chemical makeup, and it all started when the universe began, with only the two simplest types of atoms, hydrogen and helium. It is not possible to make something as complex as a human being out of just these two elements. You need more stuff. So you need things like carbon, oxygen, calcium, iron, and a host of other atoms to make a human being, or life in general. So where did these heavier elements come from, if they were not present at the start of the universe? Well, heavier atoms had been produced by nuclear fusion at the center of stars. We see much evidence that stars create new elements in the process of making energy. When stars die, and especially the ones that go supernova, they seem to recycle their material, blowing these newly made elements into the cosmos. The next generations of stars then forms from these enriched mixtures of elements, and therefore so do planets. It took several generations of stars to enrich our neighborhood, so that when the Sun and the Earth were formed 5 billion years ago, they would contain enough of the heavier atoms to make living creatures. Every atom inside of the human body, apart from hydrogen and helium of course, was once part of the inside of a massive star. And
we are all made from stardust, because all of these heavy elements are only possible to be created at the core of an extremely powerful massive star. That's the only factory that can produce these elements.
And from this process, it can create new life, not only for new stars, not only for new planets, but living, organic creatures. So, I hope that's given you a great insight.
This was amazing. I'd definitely give a like and subscribe to his channel. It was a very great.
Yes, sir.
Okay, now I'll take questions. I have some raised hands. Yeah, Sabir, go ahead.
স্যার যখন একটা স্টারের সেন্ট্রাল ফিউল শেষ হয়ে যায়, its outward pull vanishes and the gravity no longer has an outward force to balance.
Hold up. Gravity never provides outward pull. আবার বলো. Gravity no longer has, তারপর থেকে আবার বলো.
Gravity no longer has another outward force which will act against it and balance out.
Hold up. Why would you have gravity to have an outward force? Gravity is the force that is working inward.
No. I think I need to rephrase. মানে যে ফিউশন ফোর্সটা আছে না, যেটা আউটওয়ার্ডের দিকে অ্যাক্ট করে,
yes,
that vanishes because the star is out of its fuel. তাহলে এটা এক্সপ্যান্ড করে কিভাবে?
No. You're getting this wrong. One of the things that this person actually said is that in a series of very critical events, he used this phrase at certain point of this video where he did not go through these impedance spaces. So there are multiple different happening that happens within a very short amount of time in the process of a supergiant star converting into a supergiant into a supernova or hypernova. That happens to be something like this. That happens to be that when the star has lost enough mass that the inward pull is not strong enough to hold down the entire gas lump towards the sun, yet the already produced heat energy or the gamma radiation or the photons which are pushing outwards, they already are traveling outwards to continuously push on the gas molecule. So at one point the gravity becomes weak not to be able to sustain the outward pressure. That's when the outward pressure puffs up the outer layer of the gas, and because of the gravity the inner layer becomes more compressed. So there happens a separation. Some outer part of the whole star puffs outwards, and some specific beyond a certain radius of the whole star, that part become more collapsed. That happens by a series of events which is not discussed over here. I do not know the exact event series. I'm not because I didn't study about it, but there is a complex mechanism by which this happens, but this is the ultimate outcome. So the entire star basically rips off into two different outcomes. The outer layer puffs out and the inner part become more squashed,
Forming the red giant, either red giant or red supergiant.
Red giant, red supergiant. Yeah, the outer part is what is called the red giant, and the core becomes that thing, and eventually the core becomes a white dwarf, which can slowly become a black dwarf for a small massive star, and then you saw it for the more massive star. It can be either a neutron star or it can be a black hole.
Which is not in our syllabus, is it?
None of this part that I have shown you for the beyond the part of a star is formed is in your syllabus. Your syllabus only comprised of till the part the star is formed. I showed it for the sake of complete knowledge, and I find this process really fascinating. That's why I wanted to share this.
Yes, sir.
Bipro.
Sir, at some point in the video, the narrator said that the star collapses under its own weight. What does that mean?
Because of its own gravitational force. The surrounding helium, the surrounding hydrogen gas particles collapses towards the center. And that gravitational force towards the center was named as weight.
Yes, thank you.
When does that collapsing happens due to the star's own gravity? When it is turning into a white dwarf?
Yusuf, bolo. Sadman Yusuf.
Sir, here is the gravitational force actually formed due to the reason that this is a gaseous state, it is trying to attract to the centers, it's collapsing with one another. Is this the reason where the gravity starts?
No, this is the outcome of gravity, not the reason of gravity. The reason of gravity is still undetermined. Scientists could not yet properly define why gravity works. That is a part of science that we don't know yet. But the outcome of gravity is that the particles are collapsing in. So what you said is the outcome of gravity, not reason.
Oh, okay, sir.
Okay, sure.
I jumbled it, so confused.
স্যার ওই হাইড্রোজেন আর হিলিয়ামের যে রিঅ্যাকশনটা যার জন্য ওই যে হিটটা প্রোডিউস এন্ড অল ওইটা কি আর এই রিঅ্যাকশনটা আরেকবার একটু বুঝাতে পারবো?
রিঅ্যাকশনটা অ্যাকচুয়ালি আমি ডিটেইলসে বুঝাতে যাচ্ছি না কারণ রিঅ্যাকশন পুরো ডিটেইলস আমাদের নাই, বাট দেয়ার আর মাল্টিপল স্টেজেস অফ ইট. I mean, let me give you this idea in a small bit of understanding. মানে জিনিসটা তুমি ফিজিক্যালি এভাবে ভিজুয়ালাইজ করতে পারো. লেটস সে if you shoot 2 bullets from 2 identical guns towards each other and they actually hit midway in air and merge into a single pellet, they are going to simultaneously produce some spark, light, and sound, right?
Yes, sir.
Yes, sir.
In the fusion process, this is what is happening. 2 high-speed protons or 2 high-speed helium nucleus for the more massive stars, they smash into each other to merge and produce a new nucleus. And in the same process, they give out a significant amount of energy. But that energy comes at the cost of those particles losing some mass. Let's say, for the sake of discussion, let's say both of these 2 bullets had a mass of, let's say, 10 gram each. So combined mass of these 2 bullets is supposed to be 20 gram, right? Yes. But in the nuclear fusion process, whenever these 2 bullets or these two nuclei are going to merge with each other, the resulting nucleus will have a total mass that will be somewhat smaller than the numerical sum of those 2 previous values, which means the combined nucleus, freshly produced nucleus, by the merging process would have, let's say, 19 gram or 18 gram of mass. So 1 or 2 gram of mass would be missing, which will be converted into energy following the equation E equals to mc squared. And what is beautiful, that m is the mass, E is the energy, so m multiplied by c squared. C a value is light of speed of light, which is 3 to 10 to the power 8. If you square this up, you get a really large number, right? Like a extremely large number. So even from a very small amount of mass loss, you can get a very large amount of energy. That's the beauty of this equation. So that's what causes the mass to be lost. That's why the mass is lost, and that mass is converting into energy, which is being radiated out from that star outward out into the space. So that mass, so the energy is being dissipated out. So slowly a star is losing its mass property, converting it into energy, and as a result, the gravitational field is slowly becoming weaker and weaker, and eventually down the line, the gravitational force become weaker so that it cannot compress on the whole star, and further thing happens.
Okay, thank you.
Sure. Roman, আমি একটু ওয়াশরুমে যাব, so break.
Yes, sir.
Yes, sir.
Definitely. Yes, sir.
Yes, sir.
So most of the part of this lecture was not a part of the syllabus, but I really go this long way because the whole process of star formation is very intriguing. I mean, I mean, what comes at the end of this discussion is what he showed us, that the heavier particles that our body is made up from, calcium and aluminum and phosphorus, the genetic compound that we have, carbon and everything. The only location in the entire universe where these particles could have been produced by the merging of hydrogen and helium is at the center of a very powerful star. These elements being present in our body means these particles, these atoms, these nuclei were produced at the core of a very powerful star somewhere before the time, like a couple of billion or a couple of 100 billion years ago. And those things eventually got clumped together to produce the Earth. And those are in that Earth we came into existence, and evolution happened apparently. So yeah. So we are basically made from stardust. This is one of the very famous quote of Neil deGrasse Tyson, that the most amazing thing of human existence is that you have to understand that we are basically made of stardust, which is amazing because it's literally true.
Sir, in the equation E is equal to mc square, what does C represent?
The speed of light in vacuum.
The speed of light squared into a small mass gives a large amount of energy. Oh.
Yes. Okay, Polaman. So এখান থেকে একটু পড়ে যাও। Radioactivity and fission এখান থেকে একটু পড়ে যাও, আস্তে 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 পড়ে যাও, এই পর্যন্ত পড়ে আসো।
স্যার মেসেঞ্জার গ্রুপে দিয়ে দেন, ওখান থেকে পড়ি।
I want to discuss this part right now. Messenger group দিয়ে দিব eventually. So I don't want you to skip back and forth from PDF and video and PDF and video. That's why for the timing, read from the video. I mean, messenger group দিয়ে দিব. Don't worry. That can be made available.
ওকে স্যার।
স্যার এগুলো কি আপনি নতুন কম্পাইল করছেন?
এটা মনে হয় বহুদিন আগে করছিলাম, বাট আমি যেটা করছিলাম কোন একটা সেটা আমি ভুলে গেছিলাম। So I just found it, so and my memories are refreshed.
স্যার বলতে 3 বছর আগে না?
Maybe I can see the last editable date. Yeah, 17.
Yes, তাহলে ভালো। এগুলো তো স্টুডেন্ট থেকে দিছিলেন।
I believe so. পড়ো, এই পার্টটুকু পড়ো, তারপর আমি আলাপ করব। I like the smiley.
স্যার
বলো।
ক্লাসে যেতে পারি?
শিওর, সমস্যা নাই।
স্যার
বলো।
স্যার আমাদের স্কুলে পেপার 4 এর জন্য ক্লাস নেওয়া শুরু করছে।
Oh yes. I like to move it, move it. I like to move it, move it.
বাট স্যার একটা বলে দিই একটু, স্যার নভেম্বরের আগেও যদি খুলে তাইলেও বলে পেপার থ্রিতে যাওয়ার চান্স আছে।
ওকে, সমস্যা নাই। পেপার 4 যদি তোমরা একবার পড়া স্টার্ট করো, তোমার তো পেপার 3 অনেক হেল্প হবে। So, but paper 4 is easily doable in online classes, whereas paper 3 is not so easily doable on online classes. Tulan sir has some exclusive plans for how to achieve paper 3 online. So I would have to I'd like to talk to him about that. But if paper 4 is paper যদি তোমরা পড়ানো স্টার্ট করে থাকে, then I can go down that path. And the logic stays the same. তোমাদেরকে আমি বলছিলাম যে minimum time that I would personally require with 2 classes per week for paper 3 is 3 months to prepare you perfectly for your O-levels exam. বলছিলাম না?
Yes.
So so November would mean 6 months for the school. So 5 months for the 6 months for the school. Now November, December, January, February, March, April, and that might incorporate 1 class per week. And I'd say 2 classes per week. That is February, March, April. So yeah, the math works out.
Okay.
স্যার এই জন্য কি আপনি আই লাইক টু মুভির গান গাওয়া শুরু করছিলেন?
I mean, because I really can start with paper 4 with you kids online. that's possible to achieve and start. পেপার চেয়ে আমি অনলাইন তোমাদের পড়ানো স্টার্ট করতে হবে, বাট দ্যাট উড বি ভাষা বিকজ ইউ উডন্ট হ্যাভ দ্য অ্যাক্সেস টু ইকুইপমেন্টস এন্ড থিংস উড বি ভেরি উইয়ার্ড। আর আমি যদি তোমাদের ইকুইপমেন্ট দিয়ে করাইতেও চাই, যেটা আমার করতে হবে তোমাদের সবার বাসা অ্যাক্সেস করে ইকুইপমেন্ট পাঠাইতে হবে। সো দ্য হোল ল্যাব হ্যাজ টু বি বট ফর ইচ অফ ইউ and I need to send it to your house. That doesn't sound very practical. আমি তোমাদেরকে ভিডিও করে পাঠাতে পারি, ভিডিও করে পাঠালে তোমাদের দেখে শিখতে, আচ্ছা এখানে এই কাজটা করতে হবে, ওখানে কাজটা করতে হবে, বাট অ্যাকচুয়ালি করতে পারা আর ভিডিও দেখার মধ্যে পার্থক্য আছে না? ভিডিও দেখে আমি তোমাকে পেপার 4 এর জন্য পারফেক্টলি প্রিপেয়ার করতে পারবো, বাট ভিডিও দেখে আমি তোমাকে পেপার 3 এর জন্য পারফেক্টলি প্রিপেয়ার করতে পারবো না। দ্যাটস মাই আন্ডারস্ট্যান্ডিং। বুঝতে পারছি কি বলছি?
আমি যাই।
আচ্ছা ঠিক আছে সমস্যা নেই, বাকিটুকু পরে দেখে নিও, কোশ্চেন থাকলে আমাকে বলো। আচ্ছা এই পার্টটুকু থেকে কোন কোশ্চেন আছে? মানে ডিড ইউ আন্ডারস্ট্যান্ড দ্য বেসিক ডিফারেন্স বিটুইন দ্য টু ওয়ার্ডস? রেডিওঅ্যাক্টিভ ডিকে বলতে আমরা কি বুঝি এন্ড নিউক্লিয়ার ফিউশন বলতে আমরা কি বুঝি? ডু ইউ আন্ডারস্ট্যান্ড দ্য ডিফারেন্স অফ দিস টু ওয়ার্ডস?
Radioactive decay cannot be controlled or affected by external factors like pressure, temperature, etc., because these factors affect the energy of the electrons in the outermost shell of the atoms. এটা বুঝি নাই।
Whenever you think about that, you want to affect a certain pressure or you have to give a certain temperature to a physical object, which part of an atom really responds to that change? Like if you heat up a certain atom, which part of that atom really absorbs that energy? Does it reach to the nucleus? Does it reach to the first layer of electrons, or does it reach to the most outer shell layer of electrons? Which part of the atom react to that?
Because it is the closest to the heat we have supplied.
And that's basically answers your question.
Because since it never reaches the unstable nucleus, no effect happens.
So it does not get affected by that. Exactly.
আনস্টেবল নিউক্লিয়ার মানে কি?
আনস্টেবল নিউক্লিয়ার মানে কি সেটা বলতেছে। আনস্টেবল নিউক্লিয়ার মানে হচ্ছে যে একটা জিনিস বুঝো, আমি এটা তোমাদেরকে একটু ফাঁকি দিয়ে বুঝাচ্ছি, কারণ অ্যাকচুয়াল ডেসক্রিপশনটা তোমাদেরকে বলতে গেলে আমাকে স্ট্রং নিউক্লিয়ার ফোর্স, উইক নিউক্লিয়ার ফোর্স, কোয়ার্ক স্ট্রাকচার নিয়ে বুঝাইতে হবে। সো আই এম গিভিং ইউ আ ভার্সন অফ দিস এক্সপ্লেনেশন দ্যাট ইজ গোনা মেক সেন্স উইথ ইউ, which is gonna be okay for you to understand and comprehend, but you will never have to write about this stuff. So try to understand what I'm saying. Try to think about it. Nucleus is made up of positively charged particles, light charged particles, which are protons, and there are neutrons as well. Protons are naturally supposed to repel each other, correct or not?
Yes, sir.
Which means within the small confined space within which the nucleus is created, to make the protons confined within that nucleus, you have to somehow overpower that strong electrostatic repulsion force among the protons and make them clumped together, right? They are trying to repel each other and get out from each other naturally. But if you really want to make the nucleus a stable structure, you have to somehow provide a more stronger attractive force, which is going to overpower that repulsive force and make the stable structure. Does that make sense?
Yes, sir.
ঠিক আছে? For a simple example হচ্ছে, a simple example is the Royal Rumble with the steel cage around. Do you know what that is?
Yes, sir.
No, sir.
বের হইতে পারবে না।
Royal Rumble is the type of wrestling where you put 20-30 people inside a single ring and you put a steel cage around that ring. The idea is that people who get shot out of that ring, out of that steel cage, somehow either by opening the door or thrown above that steel cage, they are out of that tournament. Eventually the last man standing on the ring wins the tournament. That's called Royal Rumble.
Sir, Royal Rumble তো cage থাকে না normally. ওইটা তো
I know Royal Rumble usually cage থাকে না, but I brought the idea of cage to give you an idea of the inward force. Typical Royal Rumble cage থাকে না, but consider this is a Royal Rumble with a steel cage. So তখন কি হবে, যে all the wrestlers are trying to go out because they are continuously pushing and pulling each other, but because of the existence of the cage they cannot go out. So to make all of them confined within, you need the existence of the steel cage. Am I correct?
Yes, sir.
So that force is what we call the nuclear force, which come into play because of the existence of the neutron. In other words, I can tell you that the neutrons sort of act like a gluing substance which binds together the protons, overpowering their repulsive forces. এই পার্টটা কি বুঝা যাচ্ছে? Protons are repelling each other to break apart. Neutrons are gluing each other to keep them confined. And whenever they reach a proper balance, a nucleus is stable. if somehow that balance can becomes a bit what can I say, flickered, or it becomes a bit unbalanced, or there are reasons for that balance to be not exact, then that's what we call a radioactive isotope. For example, carbon-12 is a perfectly stable isotope. Carbon-12 is consisted of 6 protons and 6 neutrons. This is just one example. There can be there can be hundreds of other examples, but for the sake of carbon-12 is a perfectly stable nucleus, whereas carbon-14 is a bit of unstable nucleus. You might wonder, carbon-14 has 2 more extra neutrons, so shouldn't that be more stable? Like I said, I am not telling you the full story here. I'm just giving you a visualizable idea that you can work with. More number of neutrons can also make some trouble. Fewer number of neutrons can also make some other type of trouble. Both of these trouble could attribute towards an unstable nuclei. So I'm not telling you the full story here, but giving you a physical tug of war to make sense with you. So carbon-14 happens to be a bit unstable nuclei, which can break down into nuclear beta minus decay and ultimately produce nitrogen and other stuffs. Whereas carbon-12 is a perfectly stable nuclei. So যে সকল নিউক্লিয়াসের মধ্যে এই রিপালসিভ ফোর্সের আউটার টেন্ডেন্সি এবং নিউক্লিয়ার ফোর্সের ইনওয়ার্ড টেন্ডেন্সি গুলা পারফেক্টলি ব্যালেন্স থাকবে, কোনোভাবে সেটা হ্যাম্পার হবে না, ওগুলো হচ্ছে স্টেবল নিউক্লিয়াই এন্ড ভাইস ভার্সা।
Imbalanced forces result in unstable nuclei.
Yes. এই পার্টটা কি বুঝা গেছে?
Sir, the neutrons glue the protons, right?
That's half the story. That can make sense with you, but that's not the full story. I'm not telling you the full story because you wouldn't be able to understand that unless I really go deep into the discussion, which is not warranted for your syllabus. So I really don't want to do that at your level. Etute ashbe.
Okay, sir.
Second bullet point boleche je 2 or 3 more neutrons are released when an unstable nuclei is hit with a neutron. Dotted nuclei are produced. ওই অংশটা একটু বুঝাবেন?
সেটা হচ্ছে নিউক্লিয়ার ফিউশন প্রসেসের বেসিক আউটকামটা কি। Whenever we have natural radiative decay gives out alpha, beta, or gamma. These are the 3 different outcome or ionizing radiation that is obtained from natural radiative decay. And in this process, the starting nuclei converts into a different nuclei, which means your proton number changes. One nuclei becoming a different nuclei essentially means that it undergoes a proton number change, which makes one element convert into other element, because we designate the element name by the number of proton present in their nuclei. So that's the outcome for natural decay. As for the radioactive artificial decay or the fission process, let me show you an example. I believe we have some equation over here. This is the alpha decay process. This is the beta decay process. And for এখানে আছে এই যে নিউক্লিয়ার ফিউশন এখানে আছে, স্টার ফরমেশন মনে এখানে আছে, এখানে কি আছে না এখানে নাই, ব্যাকগ্রাউন্ড ফরমেশন আগেরটাতে আছে, নিউক্লিয়ার এখানে লিখি নাই কেন, ওই পিডিএফটা কোথায় রাখছে আল্লাহ জানে।
গ্রুপে দেখেন, গ্রুপে পাবেন।
দাঁড়াও, আমার পিসিতে তো থাকার কথা।
অ্যাটমিক ফিজিক্স লিখে সার্চ দেন।
না, হ্যাঁ এক্স্যাক্টলি ওইটাই করতে হবে। এখানে জাহিন্স কপির ভিতরে অ্যাটমিক ফিজিক্স ছিল। আমার সার্চ বার কই? সার্চ বার পার্টিসিপেন্ট লিস্টের নিচে ঢাকা পড়ছে, সো আই হ্যাভ টু ড্র্যাগ ইট আউট। এখানে আমার পার্টিসিপেন্টস লিস্ট আছে, যেটা তোমরা দেখতেছো না।
ও স্যার কিছু কম্পিউটারে ওটা দেখা যায়।
কেমনে দেখে এটা?
জাস্ট আমি দেখতে পারি স্যার, মাঝে মাঝে দেখা যায়। ask to unmute এগুলা লেখা আছে।
কি জানি যা হোক, আমি এখন
স্কুলেরটাতে
ম্যাজিক
আচ্ছা ম্যাজিক ফাইন, ম্যাজিক থাকো। ফিউশন প্রসেস এখানে কই? ডিকে ইকুয়েশন ইজ অফ রিঅ্যাক্টিভিটি। কি হবে নিউক্লিয়ার ফিউশন কি এখানে লেখাই নাই? এই যে ফ্লো চার্ট যেটা ছিল, এই যে স্টার ফরমেশন এখানে আছে, সেই স্টার ফরমেশনটা এখানে এখানে স্টার ফরমেশন একদম লাস্টে অ্যাড করা হয়েছে কোন এক জায়গা থেকে আইনা। একটা নিউক্লিয়ার ডিকে রিঅ্যাকশন লেখা নেই এখানে, আশ্চর্য। দ্যাটস রিয়েলি উইয়ার্ড, দ্যাটস ডাজন্ট সাউন্ড কারেক্ট।
ওই এর জন্য কি স্টার্ট ওই নিউক্লিয়ার রিঅ্যাক্টরটা ছিল?
আচ্ছা, এয়া থেকে দেখায় নিউক্লিয়ার রিঅ্যাকশন এখান থেকে দেখায়।
স্যার আপনি যে বলছিলেন স্যার ওই যে নতুন এলিমেন্টস হয় স্যার সানের ভিতর, তাহলে এই যে টনি স্টার কেমনে বানাইছিল একটা নতুন এলিমেন্ট যখন ও করছিল?
That is science fiction.
না স্যার কিছু একটা তো আছে ওটার মধ্যে, ওটা একদম
That is science fiction, right?
ওটা জানি স্যার, কিন্তু
কার্বন
ওর তো একটা
ডেটিং আমাদের এতে আছে।
হ্যাঁ, কার্বন ডেটিং আছে। আল্লাহ,
তাহলে স্যার কার্বন 14 এর ব্যাপারে তো আপনাকে ডেসক্রিপশন দিতে হবে যেটা আপনি দিতে চাচ্ছিলেন না।
We'll see about that in time. Don't worry. এই যে এই রিঅ্যাকশনটা দেখো। Check this out. This is a good one, although not so big, but it's readable. So what is happening? We have unstable uranium-233. Here they are showing the process of breakdown for uranium-233. Uranium-233 is one isotope of uranium. Typically, we prefer to break down uranium-235. Canon 235 is more preferable, but we are going to hit the uranium-233 nucleus, which is already unstable. If we allow nuclear 233 to exist in its natural state, it will preferably undergo alpha decay, and maybe some parts will undergo beta decay. I mean, it will undergo some sort of natural decay naturally because it is not very stable. But if we want to break it down at our expected requirement, let's say we require the energy, so we want to break it down right now and get the energy out of it. So we will hit that uranium nuclei with a neutron. In the speed of the neutron would be controlled in such a way, there are ways to control this, which I'm going to discuss after a while, that the neutron would get absorbed in the uranium nuclei and it will stay there. Neutron use করার কারণ হচ্ছে neutron is neutral, so the nucleus would not repel it by its own positive charges, so it can pretty easily penetrate through the empty space, and just if directed in the proper direction, because nuclei are pretty small stuffs, so if it directed towards the proper direction, it can merge itself with the uranium-233 nuclei. This will produce a very short-lived uranium-234 isotope that is given in bracket. The reason of the bracket is that will essentially happen, but the life cycle of the lifetime duration of this isotope will be extremely small, as small that it might not even be detectable. But logic tells us that if you add a neutron to uranium-233, you'll get uranium-234. So at that point, 94% of those uranium-234 will break down to give you the fission reaction. So in that fission reaction, a typical example they have given as an example. So this is not the definitive outcome. This is a one type of outcome, that in that breakdown process we are producing xenon 137, and then we are producing strontium 94. Along with these two parts, we are having some 3 free neutrons produced. And one of the examples that I can tell you is this. Let's say you have, let me give you a physical visualization which actually worked pretty well for the earlier batches. Let's say you have placed one energy plus biscuit onto the table, and you are dropping a marble from the top of the table. The marble hits the biscuit. What happens? The biscuit cracks into multiple pieces, right?
Yes, sir.
And also there will be some crumbs produced, right?
Yes, sir.
That crumb is essentially what those free neutrons are. These things are. So the beauty of this reaction is that to make this reaction happen, we have to feed one neutron, and from the process of this reaction, we are having three neutrons produced, which means actually in this entire process, for this entire process to happen, altogether, if you count out, you are producing 2 extra neutrons, right?
Yes, sir.
Because you are feeding one neutron, you are producing 3 neutrons, so altogether, which means these 2 extra neutrons that we are producing can be used to break down 2 more uranium-233 which are on the neighboring nuclei. So these 2 can break down 2 more, which can break down 2 more, which can break down 2 more. So you're going to have a geometric progression of reaction, and this process can sustain as long as there is undecayed uranium-233. So basic idea হচ্ছে এরকম, মনে করো একটা লাম্প অফ অবজেক্টের মধ্যে এক জায়গাতে আমি একটা নিউট্রন দিয়ে হিট করলাম, that is going to produce 2, and that 2 is going to produce 4 is going to produce 8 is going to produce 16, and in this way the entire uranium-233 lump or piece is going to undergo really rapid breakdown because of the presence of all those free neutrons. This is what we call a chain reaction, that once started, it can sustain itself through the endpoint. যতক্ষণ পর্যন্ত আনডিকেড ইউরেনিয়াম 233 থাকবে ততক্ষণ পর্যন্ত সে ব্রেকডাউন করে এগুলো প্রডিউস করবে and you will release a huge amount of energy over a very short amount of time, so the power would be extremely high, and explosives mean that they have extremely high power. Try to understand, using fuel we can run cars. That's a controlled use burning of fuel. Using a fuel we can make explosion. That's an uncontrolled version. Uncontrolled version is simply ki hoy, rate of energy release is very high, you produce a huge amount of heat energy over a short amount of time. That's explosion, right?
Yes, sir.
So if
Yes,
you
sir.
so if we allow the chain reaction to sustain and allow to continue further, that's going to produce a huge amount of energy. This is the mechanism for a nuclear bomb. Whereas in the nuclear reactors, where we use nuclear fuel to produce electrical energy, we somehow remove some of these free neutrons by some mechanism. Key mechanism shall I to pore boltesi. We somehow remove some of these neutrons so that they cannot take part into the consequent process. So we control exactly how many neutrons will be allowed from every reaction for the further decay process. So that process can be controlled from 2 to 2, another 2, another 2, another 2. We're not going to allow the exponential breakdown of 2, 4, 8, 12, 8, 16. Eta আমরা allow করব না. We're going to remove some neutrons from the reaction environment so that it will be a control process, like the way fuel is burned in the car. বুঝতে পারছি? মানে সিমিলারিটি গুলো বোঝা যাচ্ছে?
Yes, sir.
Yes, sir.
সাবির কোনো কোশ্চেন?
Yes, sir.
Sir, I did not fail to catch the similarity between the fuel burning in car and this reaction.
When fuel is burned, we are burning a large amount of available fuel in a controlled manner, slowly, so that you are having a limited amount of power that is converted from chemical energy into kinetic energy, which is useful for you, by which you can run the car. But if you shoot a bullet into the fuel tank, the entire fuel tank goes up into flame in a single second or in a single fraction of second. That rate of energy output is explosion, which is not controllable and you cannot capture that, so it's basically destructive. So that's what I meant, that if we allow the fusion process to happen uncontrollably, then that exponential increase of breakdown will happen, and that will be denoted as chain reaction, which is a basic mechanism for a nuclear bomb, where you require a huge amount of energy output over a short period of time. Basic idea of explosion. And if you want to use it for a useful purpose, for example, for the case of a nuclear reactor, where you will use nuclear energy to boil up some water and run some turbine and produce some electrical energy, then you need to have that energy released in a controlled manner so that you can absorb that energy,
Capture them, and you actually put them into useful work.
Exactly.
If it's uncontrolled, then we will not be able to capture the energy for work, and those energy needs to do some work. And therefore, the work they do is what we do not want, destruction.
Exactly. Perfect.
স্যার তাকে বলো স্যার মেল্টডাউনটা তাহলে এর সাথে কোনো রিলেশন আছে? ওই যে মেল্টডাউন বলে যে কি জানি ঝামেলা হয়, রেডিয়েশন ছড়ায় যায়।
চেরনোবিলে যেটা হয়েছিল ওটা হচ্ছে যে in a nuclear reactor you should have proper systems in place that would be able to check onto the breakdown process so that you do not have the reaction ever reach uncontrollable state. Because a nuclear reactor has all the equipments available to become a nuclear bomb. The only reason it does not become a nuclear bomb because we control the reaction not to become the nuclear bomb. Right?
Yes, sir. Yes, sir.
So if at any point of time of operation, those control mechanisms, they are redundant scenarios, but let's say they all fail one after another, which lead to the scenario that those control factor is removed or it's not working anymore, then your entire reactor can become a nuclear bomb, potential nuclear bomb. That is what we call a meltdown.
স্যার কিন্তু চার্নোবিল তো এটা তো এক্সপ্লোড করে নাই।
Yeah, it does not explode because it has huge amount of water available within the system, which is used to take out the energy. That entire amount of water, it did not get evaporated, so it did not explode outwards, but all the nuclear nuclear waste which is produced from the nuclear reaction. For example, in this case you can see that this xenon and also the strontium, they are the nuclear waste. We call them nuclear waste because these are also radioactive substances which has a pretty small half-life, so that they would radiate alpha particle, beta particle over a really long amount of time. but they cannot be used in further fission process. মানে জিনিসটা আমি তোমাদেরকে বুঝাই, জিনিসটা আমি তোমাদের নরমালি বুঝাই। মনে করো, আমি খুব সিম্পলি একটা জিনিস বুঝো, মনে করো বেসিক এনার্জি প্লাস বিস্কিট ভেঙে দাঁত দিয়ে ভেঙে খাওয়া যায়, ঠিক আছে? ঠিক আছে, টোস্ট বিস্কিট এর থেকে আর একটু শক্ত, সেটা দাঁত দিয়ে ভেঙে খাওয়া যায়, আচ্ছা ফাইন। আর মনে করো আমি একটা সামহাও একটা সার্টেন একটা এক্সট্রা চিনি দিয়ে আমি একটা কেক বেক করলাম, যেটা পাথরের মতো শক্ত হয়ে গেল, দাঁত দিয়ে ভেঙে খাওয়া যাচ্ছে না, ঠিক আছে? Let's say it still has food equipment within itself, but it is not edible. But if you put it into a, let's say, a wet environment for long enough, maybe it will become edible, but it is not edible at the time being. What I'm trying to mean is that stuffs which are easily breakable and easily obtainable out energy out, you can break them readily as you want, so that will not that will cease to exist and convert into something else. But stuffs which are still bad but cannot be break down easily, those are these stuffs, xenon and strontium. These things are still bad, they produce radioactive decay, natural radioactive decay, but they cannot be artificially broken down. And because you cannot artificially they have enough unstability to produce natural radioactivity, but they don't have enough unstability for us to be able to break them at our will.
মানে এফিশিয়েন্ট না এটা,
মানে এটা ব্রেকডাউন করতে হলে তোমার মানে অনেক কিছু হলো পাওয়ার করতে হবে। এই আমাদের এই টেকনোলজি নাই, বা হিউম্যান স্পেসিস এখন এই টেকনোলজি অ্যাভেলেবল করে যেগুলোকে ফার্দার ব্রেকডাউন করা পসিবল। মানে দিস ইজ মোর স্টেবল কম্পেয়ার্ড টু দিস ওয়ান, দিস ইজ অলসো মোর স্টেবল কম্পেয়ার্ড টু দিস ওয়ান, বাট দে আর অলসো রেডিয়েটিভ, which means they are going to emit out alpha radiation, beta radiation, gamma radiation with quite a huge amount of for a really prolonged amount of time. And this is what makes them radioactive waste, because they are not useful as radioactive material anymore, but we cannot simply allow them to go into regular environment, because that will pollute the entire environment. So what happened in the meltdown process is that there was a rapid production of these materials which did not puff out like a nuclear bomb, because there were some control mechanism or residual control mechanisms were there, but these things start to puff out or evaporate out and got carried down by the wind to other neighboring countries, which got those people of those country undergo cancer, then the kids were born with prenatal diseases, congenital diseases, and those kind of problems.
Yes.
আচ্ছা স্যার, what radiation, যে ধরেন this xenon strontium তাদের radioactivity they shoot out some stuff, alpha beta gamma radiation. What is this? Subatomic particles which combine with other atoms and basically make them unstable
মতো নাকি
or something else.
আমি কোশ্চেনটা বুঝি নাই, আরেকবার বলো, কোশ্চেনটা বুঝি নাই।
স্যার রেডিয়েশন করলো, ঠিক আছে,
হ্যাঁ,
রেডিয়েশন করে আলফা বেটা গামা পার্টিকেল রিলিজ করলো, আর দ্য পার্টিকলস, what are these particles? Subatomic neutrons, subatomic protons, electrons, or what?
Yes.
Which one? Neutron?
Well, exactly which of these, because this is an example of the outcome. So to be honest, there will be a mixture of a lot of different elements and a lot of different isotopes, each of which are going to have different amount of life, different amount of half-life. Now, which is going to undergo exactly alpha decay, or which is going to undergo beta decay, or there can be some isotopes which is going to undergo alternately alpha or beta decay. Let's say there might be a proportion. Let's say there can exist some isotope for which, let's say, 75% are going to undergo alpha decay and 25% are going to go beta decay. That kind of mixture is also possible. Like I said, that I didn't tell you the whole story of the imbalance. The imbalance comes from a very critical combination of factors, which I did not tell you. So those factors will determine what kind of radioactive decay they are going to give. It can be observed and detected, but it cannot be pre-calculated or cannot be controlled.
Yes, sir. Acha, sir, the three types of radiation that a radioactive particle can give, alpha, beta, gamma, does different types of them give out different types of subatomic particles? We need to know those factors.
No, you just only need to know what the alpha particle, alpha, beta, and gamma particles are, which is going to be next part of our discussion, which I can go to, which is right over here. And এক মিনিট পড়াশোনা করো।
Sir, is this the reason you don't want a nuclear power plant in Bangladesh?
শোনো, যে দেশে আমাদের হসপিটাল থেকে ইলিসিট সার্টিফিকেট দিয়ে প্র্যাকটিক্যালি মানুষ মারার প্ল্যান করার জন্য কারোর এখনো সুনির্দিষ্ট শাস্তি হয় না, এবং যে দেশে স্বাস্থ্য মন্ত্রণালয়, মানে আমাদের দেশে এরকম প্রবলেমগুলি আছে, সেখানে কিভাবে আমি এক্সপেক্ট করতে পারি যে বাংলাদেশে একটা নিউক্লিয়ার প্ল্যান্ট সাকসেসফুলি প্রপারলি রান করা যাবে? Can you picture it? I cannot. As a I'm not going to say I'm highly educated, I'm not going to say I'm highly qualified, but as a regular person who understands as even a little bit of technology, I cannot picture a properly running, properly maintained, properly supervised nuclear plant in Bangladesh. I cannot picture that. এই পার্টটা পড়ো সবাই দ্রুত
স্যার
বলো।
স্যার রেডিওঅ্যাক্টিভ ডিকে যে আয়োনাইজিং রেডিয়েশন এটা মানে কি?
এটা নেক্সট ক্লাসে বুঝাবো, সমস্যা নেই। কালকে ক্লাস আছে না আমাদের?
না
কালকে তো শনিবার।
এরপরে ক্লাস কবে? হ্যাঁ তাহলে সানডেতে বাকিটা পড়ো। আজকে এইটুকু পড়ো, এইটুকু বুঝে আমি ছেড়ে দিচ্ছি তোমাদেরকে। জাস্ট ডেফিনেশনটুকু পড়ো এবং এই রিঅ্যাকশনগুলি বুঝো। এই নাম্বারগুলোর এক্সিস্টেন্স তোমরা কেমিস্ট্রিতে শিখছো। আপার লেফট নাম্বার রিপ্রেজেন্টস দ্য মাস নাম্বার, দ্য লোয়ার লেফট নাম্বার রিপ্রেজেন্টস দ্য প্রোটন নাম্বার, আপার রাইট নাম্বার রিপ্রেজেন্টস দ্য আয়নিক মানে লস অফ ইলেকট্রন, মানে কোন টাইপের আয়ন, এন্ড লোয়ার রাইট নাম্বার রিপ্রেজেন্টস দ্য নাম্বার অফ অ্যাটমস ইন এ মলিকিউল। ইউ নো দ্য ফোর পজিশন নাম্বারস, রাইট?
Yes sir. মানে পিরিয়ড টেবিল দেখা লাগে মনে রাখার জন্য।
তোমাদের এগুলো কিছু মুখস্থ করা লাগবে না, কোনটা কি মিন করে সেটা বুঝতে হবে। সো ফর নিউক্লিয়ার রিঅ্যাকশন, দ্য টপ লেফট রিপ্রেজেন্টস দ্য মাস নাম্বার হুইচ ইজ দ্য কম্বাইন্ড নাম্বার অফ protons and neutrons, the lower left represents the proton number only, or something that's also called the atomic number. পড়ো, এটা পড়া শেষ করো জলদি।
স্যার আমি এটা বুঝতে পারিনি। Resulting nucleus has 4 nucleons short.
Yes, because the alpha particle is taking out 4 nucleons. Each of the particle, proton or neutron, which is exist in a nucleus are called in generally nucleon. For example, মনে করো ক্লাসরুমে আমি ধরো তোমাদের 50 জনের সাথে ক্লাস করতেছি, ইনক্লুডিং মানে 50 জন স্টুডেন্ট এবং একজন আমি। So if he asks how many people are inside the class, the answer will be 51. So how many humans are in the class? 51. How many of them are teacher? 1. How many of them are student? 50. Like that. So all the particles which are present in the nucleus are called nucleons.
বুঝিছি স্যার।
বলো।
আপনি কি আলফা ডিকে বেটা ডিকে এগুলো কি এখন পড়বেন নাকি নেক্সট ক্লাস?
আমি সেই ডেফিনিশনটুকু পরে আসলে ছেড়ে দেব। ইকুয়েশনগুলো তোমাদের পরে দিছি, এই নোটটা আমি তোমাদেরকে দিয়ে দিছি, ডোন্ট ওয়ারি। নোট তোমাদের এই নোটটা বেসিক্যালি হোয়াট আই বিলিভ হচ্ছে আগের যে হ্যান্ড রিটেন নোট, ওটা টাইপ ভার্সন, বাট ইউ ক্যান হ্যাভ অ্যাক্সেস টু বোথ অফ देम। আই রিয়েলি ডোন্ট মাইন্ড।
আলফা ডিকে বেটা ডিকে কি হচ্ছে এগুলো তো এখন বুঝাবেন না?
না না না, এগুলো রিঅ্যাকশন এখন যাব না, আপাতত জাস্ট ডেফিনিশনটুকু বুঝো।
ওকে।
মানে যতটুকু দেখতেছো ততটুকু বুঝলে হবে। এরপর এটাকে নিয়ে ফার্দার কি ক্যালকুলেশন করবো সেটা নেক্সট ক্লাসে দেখাবো। যতটুকু দেখতেছো এক্স্যাক্টলি ততটুকু বোঝা যাচ্ছে কিনা তাহলেই হচ্ছে।
স্যার নেগেটিভ অ্যাটমিক নাম্বার আবার কি?
নেগেটিভ অ্যাটমিক নাম্বার কি বলতেছি, একটু সবার পড়া শেষ হোক। I'll give you everyone one more minute to finish the reading. I'll come to your question, I'll answer it.
Sir, why do this, like why denote an electron as a beta particle and not just an electron?
I'll answer this as well.
Sir, if the physical properties are identical as an electron, then isn't it an electron?
It is electron, but it has a different reason for it to be called beta particle. I'll tell you that in a bit. Okay, that's enough time to finish the reading. So আমি কয়টা জিনিস বলে যাই। এক নম্বর জিনিস হচ্ছে যে এখানে যে বেসিক পার্টটুকু আলাপ করা আছে আলফা পার্টিকেল নিয়ে, আলফা পার্টিকেল এই ইকুয়েশনটা সবাই বুঝছো? এই এন এর ইমপ্লিকেশনটা কি বুঝা গেছে?
Yes, sir. Number of decays equals
নাম্বার অফ আলফা পার্টিকেল রিলিজ। সো একটা পার্টিকেল থেকে যদি একটা আলফা পার্টিকেল রিলিজ হয়, ইন দ্যাট কেস এগুলা 4 আর 2 করে কমবে। বাট যদি দুইটা রিলিজ হয় তাহলে এটা 8 এবং 4 কমবে। তিনটা রিলিজ হলে এটা 12 এবং 6 কমবে। So you have to multiply this n number over here to make the subtraction. That's the important factor. এটা হচ্ছে একটা জিনিস। Beta decay basic process হচ্ছে one neutron will be converted into one proton and one electron or one beta particle will be released. Electron and beta particle are identical stuffs. The only reason we call a beta particle is because of where it was created or from which position where did we find it in the first place. This, I mean, one of the examples that I can tell you that all the people in the world, human beings, they're all Homo sapiens, but based upon their nationality, they can be Bangladeshi, Indian, Sri Lankan, Maldives, USA people. They can be a lot of different people, right? But do you think in all of their chromosomal capabilities or as compared to species, Bangladeshi person is highly different than an Indian person in their chromosomal capabilities, in their biological definitions? They are not different. That's basically it. So electrons which you find in the orbits, they are named generically as electrons. Electrons which are produced in the process of a beta decay are called beta particles. The physical difference is that if you observe any electron that exists in an orbit of an atom, the amount of individual energy that electron will have is a certain value, whereas if you actually physically observe a beta particle that was shot out of a radiative decay process, that energy of the beta particle is going to be millions of times higher compared to the typical energy value of an orbital electron. Beta particles are extremely energetic compared to orbital electrons, but their physical properties are exactly same: mass same, charge same, behavior same, everything else is exactly identical. They are both the same thing, but depending upon their birthplace and the energy amount, they have different names. That's it.
স্যার আলফা পার্টিকেল ইকুয়েশনটা আমি গ্রাস্প করতে পারি না, আপনি কি আরেকবার বলবেন প্লিজ?
কোন পার্টটা বুঝো নাই বলো, আমি ওই পার্টটা বুঝাচ্ছি। ফার্স্টের ইকুয়েশনটা বুঝছো?
Yes, sir. Because for one alpha particle coming, there will be the resulting nucleus will be 4 nucleons short. Kintu in number decay, a numberটা and the equation, ওই অংশটা আমার confusion.
In number হচ্ছে that if you have more than one alpha particle coming out of a radiative nuclei, let's say if you have 2 alpha particles coming out of a radiative nuclei, one after another, then what would be the resulting nuclei should look like?
That would have nuclei should be 8 nucleons short then.
That is represented as 2n.
Oh, so where n is the n number of decays, that means if n number of alpha particles come out, then the resulting nuclei will be 4n nucleons short, 2n protons short.
Exactly.
That means 2n neutrons short, right?
Sir, আমারও এখানে still
নিউট্রন কতগুলো শর্ট হবে সেটা আমার হিসাব করে বলা লাগবে। I'm not sure about the neutron number. I have to write the equation and calculate. I cannot do this mentally.
Oh, because আমি চিন্তা করছিলাম যে নিউক্লিয়ন হচ্ছে প্রোটন প্লাস নিউট্রন, আর
Exactly, you're correct.
তাহলে 4 minus 2 gives 2 neutrons lost. So I'm not sure what complexity is there for which you are unable to calculate mentally. If it is in our syllabus, then
No. I'm a bit preoccupied with something else. I'm doing something else alongside doing the class. That's what.
Oh, okay, sir.
No. This is not something that I like to do, but I'm really doing it because I don't like to do it. It doesn't make sense. Anyway, the resulting nucleus will have in terms of proton hold up, 2n number of protons short. Yes, because each helium nucleus has 2 protons and 2 neutrons. So it would lose 4n number of nucleon, 2n number of proton, and 2n number of neutron. Yeah, you are correct there.
White key,
yes, sir.
Well,
white key, sir.
Why is the symbol for that atom? Aluminum hole aluminum, zinc hole zinc, cobalt hole cobalt. whatever that you have as aluminum. Y represents the symbol of that element, which in this case is represented as an arbitrary thing. I'm not naming that thing.
The new atom will be formed beside the helium atom.
কি বলছো আবার বলো, and
The
listen to
new-
your question as you ask it. বলো.
Alpha particle. A new atom will be formed beside the alpha particle. Along with
Beside the alpha particle, not inside the alpha particle, beside the alpha particle. So এখানে একটা ইন্টারেস্টিং জিনিস হচ্ছে যে মনে করো let's say if we start with a lump of this material of an object that is going to undergo alpha decay. In the process of alpha decay, we say that in that process of alpha decay the original element is decayed, and decay হয়ে কিন্তু এটা vanish হয়ে যাবে না. This would still be present in a different element. So what I'm trying to say is that let's say if you have a 1 centimeter cube of a certain substance which is undergoing alpha decay, এটা যখন half life পার হবে, half life is the amount of duration within which half of the nuclei undergo decay, এই পুরো জিনিসটা কি দেখতে অর্ধেক হয়ে যাবে? would half of the mass of those atoms would be vanished? Is it so? The answer is a solid no.
No, sir.
It would still appear to be same. Only the number of available nuclei within that material or number of element or amount of element within that cube would half of it would be the original thing, half of it would be the newly freshly produced thing. So you'll have 50% 50% each. The whole cube is not going to become half in size or half in mass. Decay process does not vanish a particle. Decay process converts one thing into another. এইটা বুঝো. Sometimes kids misunderstand the idea of decay. Decay does not mean the particle is becoming vanished. Decay means the particle is becoming something else. বুঝতে পারছি?
We can compare it to like this way, the radioactive particle is an unstable cube which breaks down half into one element and maybe quarter or 1617 breaking down into the different n number of helium nuclei.
Exactly, and whenever this nuclei would be whenever the the ionizing radiation that will be produced out of this, the ionizing radiation that will be produced out of this breakdown process, if it's possible that those ionizing radiations are going to come out, they're going to come out and can be detected outside this cube, which is possible. But if some ionizing radiation get trapped within this particle, then they're going to remain as trapped. Remaining trapped means that if let's say if this material is alpha decay material, then if some alpha particle cannot come, let's say at the very center at the very inside or at the center of this cube, some particle underwent alpha decay. Now, for the alpha particle to be able to come out of this cube, it has to penetrate through a huge thickness of material, and then it can only come out of the cube. Let's say that did not happen. Alpha particle got absorbed or stopped after covering a small bit of distance. After it got produced from the radioactive decay process. In that case, that alpha particle would take 2 electrons from any of the neighboring elements because it can, and convert itself into a helium atom and stay within this cube. This is why in many cases uranium ore can be found with helium gas present in them, because typical helium atoms produce alpha decay, and whenever these alpha particles cannot be released from the particle directly into the atmosphere or the outside the object, they would get stuck over there. And whenever they are stopped, the helium nucleus would not remain as helium nucleus because it is highly positively charged. It will somehow steal 2 more electrons from the neighboring elements and make itself convert itself into a helium atom, and it will remain as that.
That means there is a uranium lump which has done some radioactive decay and alpha particles came out, but they were unable to escape that lump. They were stuck in the lump. So from that lump system's electron system, it took some electrons, became helium gas and stayed in the lump. Right?
Exactly. So that means that if you have naturally occurring uranium from an ore, you should always expect some presence of pure helium atom in that part. This is one of the key ways by which radioactive isotopes are searched or they are explored underground, that scientists look for atomic helium present in different parts of the world by doing some scanning mechanism, and if they found that there is a significant concentration of helium atom in a place, they can explain that, well, if there is helium atom, there might be some element which is producing alpha decay. Alpha decay should come from some radioactive isotope. So let's dig in. That's when they dig in and look out for the actual substance. They don't directly detect the uranium. They first detect the atomic helium presence. For a certain high amount of concentration of atomic helium, they go ahead and dig out the material to look out for radioactive substances.
So this is how
Sir,
the
how is this
radioactivity
harmful?
detectors work.
একজন করে বলো।
Sir, precautions need to be taken before getting close to this radioactive material.
Definitely, always প্রিকশনস গুলো আমি নেক্সট ক্লাসে বলবো, আমাদের ইউজেস এবং প্রিকশনস গুলো পরে আসবে ডিটেইলসে, তোমরা নিজেরা পড়তে পারো, সমস্যা নাই, বাট আমি ডিটেইলসে আলাপ করব নেক্সট ক্লাসে। হ্যাঁ, ইউসুফ বলো।
Sir,
আপনি কি কোশ্চেন উইল কল
is this
ডিটেইল?
how radioactive detectors work?
I did not say how the radioactive detectors work. I said that the detector looks out for helium, helium nuclei. I didn't say the mechanism of the detector. I said what is looked for.
Okay, is this what the detectors initially look for?
Exactly, helium nuclei.
Okay, sir.
মানে জিনিসটা হচ্ছে অনেকটা এরকম যে মনে করো তুমি বাঘ খুঁজতেছো, এখন বাঘকে ডিরেক্টলি খোঁজার থেকে যে সকল জায়গাতে বাঘের পায়ের ছাপ আছে ওই সকল জায়গাগুলো হচ্ছে বাঘ আছে এই এলাকা তার প্রিকারসর। So if you have significant concentration of atomic helium at a location, you can expect there should be some alpha particle producing isotopes present around. So that's sort of an example that I think works. বুঝা গেছে?
Okay, sir. স্যার আপনার এখানে একজন স্টুডেন্ট আসছে, অ্যানোমিয়াস স্টেবল সল্ট।
আপনি
Kids, thank you very much. Good night.
স্যার